Okay, very good. Good afternoon, everybody, and a warm welcome to our webinar on innovations in integrated floating offshore wind systems, together with our Corewind Project partners. So thank you for joining, both to the speakers and to our participants. My name is Sabina Potestio, and I'm a project manager in energy policy at Wind Europe, and I'm in charge of the dissemination and communication of the Corewind project. So apart from Wind Europe, the Corewind Project Consortium includes many other companies and research partners. So today we'll be telling you a bit about what we've been up to in our project in the last year and a half or so. And this will be done by our experts from some of our partners in the consortium. So very packed agenda. From Wind Europe, we have Liseta Ramirez. From IREC, we have Jose Luis Dominguez and Jose Ignacio Rafa. From University of Stuttgart, we have Mohammad Youssef Mahfoud, Clement Mollins from UPC, Valentin Aramounet from INOCI, Marie-Antoinette Schwarzkopf from Ramboll, but also a guest speaker from Vestas, Pablo Necochea. So you might have already heard about the Corewind project. It aims to achieve significant cost reductions and enhance the performance of floating wind technology through research and optimization of mooring and anchoring systems and dynamic cables. The Corewind project started in September 2019 and is being funded by the European Commission, and it lasts 3 years and a half. But you can actually find more information about the project on our official website, corewind.eu. So you'll find there a bunch of reports on all the different work streams which we're working on in the project, but also more information on the Corewind project partners. So before starting, just a few words on the Q&A session, which we'll have at the end of the presentations. So it will last 20 minutes, and you can type in your question in the question box like you see here on the slide. And along with your question, please also type who you want to direct the question to, so it also makes it easier for me to address the right person. So without further ado, let's start off with giving a bit of an overview of where we stand with the floating offshore market today and related policy in Europe, also just to frame our discussions. So my colleague Liseta Ramirez from Wind Europe will be doing that, and she's our analyst on offshore wind. So over to you, Lisette.
Thank you very much, Sabina, and welcome everyone. Thank you for hearing us today. So let's take a look at a bit of what's happening in Europe in terms of policy development. Europe is leading the floating wind movement, and we have currently over 80% of all of the installed capacity in the world. The photo that you see now, it's the currently operating turbine, the largest in the world. It's 8.4 megawatts. This is as big as 2 times the Statue of Liberty, just to give a bit of an overview to compare with something else. So one rotation of this turbine, it's enough to fill the electricity demand of a household for a full day. And this project is located in Portugal. Now, because the European Commission recognizes the importance of floating wind and of offshore wind as a sector in Europe, in the next slide, I'll show you how now we have a dedicated offshore renewable energy strategy. This is, of course, in the context of our European Green Deal. This is the plan on how Europe is going to decarbonize the whole economy. This strategy is focusing especially on the scale-up of offshore technologies. This includes bottom fixed, floating, and other technologies like wave and tidal. So in order to do so, the European Commission is focusing in 6 different aspects. These include the maritime special planning, the grids infrastructure, to have a regulatory framework for the EU, to have enough private and public investments, which actually amount in total 800 billion euro up to 2050. Also, the research and innovation sector, and of course, the supply and value chain. So, through these 6 areas together, the scale-up of offshore wind is going to be up to 60 gigawatts by 2030 and 300 gigawatts by 2050. To set a bit of context, if we add up also the ambitions of the UK and Norway, by 2050, this is going to be over 400 gigawatts in total. At the moment, we have 25 in all of Europe. So now, to deliver all Europeans with renewable electricity, we need not only bottom fixed, which is our main source of electricity from offshore today. We also need floating offshore wind. This is a very interesting map. So let me explain you a bit. If you take a look here, this is all of Europe barometry. So we see the water depth in different regions. As you can see here, everything that is mostly in red is suitable for bottom fixed technology because it's up to 50 meters water depth. The rest, especially those that you see in yellow and green, are more suitable for floating technologies, with the water depths going between 50 to 150 or even more. And actually floating can go even deeper. Now, if you look especially in this map to the south of Europe, to deliver renewable electricity to all Europeans, we need to have a special focus in the Mediterranean Sea. Actually, the European Commission has also conducted a study where they show that floating offshore wind is the most suitable technology to be deployed in the southern European waters. So these ambitions that we will have between 70 to 75 gigawatts of floating technologies by 2050. At the moment, we don't have any project operational in the Mediterranean Sea, but we will have 3 projects coming online by the end of 2023. So we require a massive scale up. So in the long term, up to 1/3 of all of the technology in offshore will be floating. Now, at the moment, in the next slide, I show you how we have a pipeline worth of projects of at least 7 gigawatts that we are sure the industry can deliver at a cost of 40 to 60 euro per megawatt hour. But this is only going to happen if we have the right policy framework that will remove also the barriers to mass deployment. And also to mention, this 7 gigawatt pipeline is mostly led by 3 countries, Norway, France, and the UK. But there are others, of course, from the Southern Europe also shipping in. Now, what is it that we need then to move forward in terms of the regulatory barriers? Well, I will show you now in the next slide what is the right framework for delivering floating offshore wind farms. We want to have enough visibility for the supply chain to be ready to deliver these large projects. This requires to have a clear auction timetable, which means we want to have technology-specific auctions because the technology still needs to have one more step towards cost reduction. This is also possible to achieve with a model using contracts for difference. This is currently the best model to provide stable revenues. Actually, banks today are willing to lend up to 80% of all of the upfront costs when using CFDs. Also, we want a one-stop shop for permitting. This is going to make all of our permitting process much faster and with a single authority. It's also much more transparent. We need then to ensure that there is enough development for the grids. This requires both private and public investors. And of course, we're going all this through ensuring a happy coexistence with other sea users, so not only dedicated to offshore wind. So, to conclude, I want to show you in the next slide how we are delivering this. So we are delivering floating wind farms in the future, which requires us to link currently our innovations, which is the research and innovation sector, with the applications, which is the supply chain and industry applications. And the way to do so is through the right policies. So together, this is how we can deliver to scale up floating wind to deliver renewable and affordable electricity to all Europeans. Thank you very much.
Thank you, Lisette. So I would say that's the perfect way to set the scene, and also goes to show how research and innovation projects like Corewind are so important to support the development of the floating market in the years to come. So now let's move on to properly introducing the Corewind project and its objectives. So I mentioned them briefly at the start. So I hand over the virtual mic to you, Jose Luis Dominguez from IREC, and who is also the coordinator of the Corewind project. The floor is yours, Jose.
Thank you so much, Sabina, for the introduction. Hello, everyone. Now, what I will do is briefly introduce you to Corewind. Corewind project is an European-funded project, which the consortium which is developing that project is shown in that slide. So we are trying to cope with all the value chain within Europe, okay, for floating wind. So we are covering academia, industry, also people related with developers. We have manufacturers and so on. So we believe that thanks to the development that we can do and with the knowledge within the consortium, we can really make something new and something valuable for the whole industry. Then also we have a really nice advisory board helping us to cope with some existing gaps that we have on the consortium. So we have knowledge and support from Carbon Trust, InnoEnergy, DIM, NREL, and Winkery. So then if we move to the next slide, we can talk about which is our key objective. Okay, so as a project, let's say, our idea of Corewind is really to go beyond the state of the art of floating technology. So what we really want is to develop and validate innovative and cost-effective technologies. Okay, and keeping in mind that what we want to do is not like take existing concepts and just bring in to floating, but try to develop floating-wise technologies. Okay, and then this is something that at some point can lead us to a breakthrough ideas. So if we move on, one of the key objectives here also is how we are approaching that objectives. Okay, so what are the key challenges, as also related with Lisa's presentation previously, is what are the key challenges on floating. So we have key challenges on cost, reliability, industrialization, and so on. So to this regard, we are try to cope with different technologies and innovation procedures. So we will work on digitalization, okay, which is really important to increase or keep really nice reliability and operational maintenance. So on, we will work on high multi-fidelity advanced models because we really need that advanced models in order to cope the whole design and construction phase. And then we are working on optimization of mooring dynamic cables and so on. And something that sometimes is not that considered within EU projects, at least on the research ones, is like the importance of industrialization and standardization. And this is something that we are strongly considering within Corewind, okay? Because what we want is really to make it happen, that our innovations will reach the market at some point and will help. And so, of course, that industrialization will come later on, so in a few years probably. But what we will provide, at least at the end of the project, will be some open data, open models, new designs, and of course some knowledge and guidelines, you know, in order to ensure that forthcoming innovations to become true. Then, if we move in order to detail a bit what are the coming or the expected impacts, okay? So of course the key objective within floating wind is just to reduce the cost. So we want to go beyond a reduction of the LCOE of 15%. Of course, it can be done with different approaches and from different innovations. And then what we will do is like to take advantage of most of them and put them together. So we will go from upscaling. Of course, we are working already with the 15 megawatt wind turbines. We will work on shared moorings and optimize and integrated designs for also dynamic cables, improve operational maintenance strategies, including digital twins and so on. And finally, also include a wind farm lifetime. So we want to extend it up to at least 30 years through the appropriate digitalization techniques. Okay, and then in that part, we will provide some nice tools and key reference documents to help the value chain. So if we move to the next slide, we will see where we are now, and somehow it will introduce the coming presentations that we will see. Okay, as Sabina said, Corewind project, okay, it's now on the month 18. So of course, we are expecting to provide much more outcomes and more detailed results. But up to now, what we can offer and we can already present are our reference models. So of course, probably you all know the 15 megawatt reference from the NREL. And then also we have already available 2 floater models. So you can just try to use them if you want. And as well, we have some economic tools that will be available soon, like for an LCOE calculation tool and so on. And finally, we have already some public reports and deliverables. Then more details on that resources and outcomes are on the next slide. So you can see here that you can go to our web page, as already Sabina tell you. So in corewind.eu publications, you will find out all that reports. So we have quite a bunch of them, and I think they are quite interesting and useful. And then also, if you visit our Zenodo community, you will find out there not only the reports that are available in both sites, but also the models. Okay, so you can download it for OpenFast and use the Winkery and the active float models for the analysis. So the only thing that I can just tell you is like you will see in the coming presentations that some results that I'm presenting here, details may come later with the reports if you want to investigate it, and feel free to ask anything or any doubt that you may have. So thank you, and please join the conversation and join us on Twitter, follow up on LinkedIn and Twitter and so on. Good. Thank you.
Thank you very much, Jose. I think that gives us a very good overview of what the project is all about. So going over to Climent Molins from Universitat Politècnica de Catalunya and Mohammad Youssef Mahfoud from University of Stuttgart. So they will be telling us about the floating OpenFast model for the UPC concrete spar floater designed for the IEA wind 15 megawatt reference wind turbine. So over to you guys.
Thank you very much, Sabina. This is Climent Molins. I will introduce the Winkery concept to you all. As already said by Jose Luis and also Sabina, this is an spar platform, but it is an integrated concept that includes both the tower and the floater without any joint in a monolithic structure. So in this way, it has some advantages, and also it has some challenges, of course. But this produces at the end a more durable structure that at the end this is quite interesting. Of course, the material in this case, as also the other platform used in the Corewind project, is made of concrete, reinforced and post-tension concrete. And for the particular case of the 15 megawatt wind turbine, the strength of the concrete is the 80 megapascal. Of course, as a spar buoy system, it is ballast stabilized. In the next slide, we can see one of the characteristics of looking for low cost or cheaper and reducing the LCOE and so on. We can take advantage of using some materials, like for the ballast. In this concept, we propose the use of black slag from electrical furnace. This is a byproduct, and it is possible to achieve easily bulk density, a bulk specific weight of 25 kilonewtons per cubic meter, which is not so much as we can obtain with other materials, like magnetite. However, has the advantage that is significantly cheaper, as the estimated cost already placed would be around 35 euros per ton. In the next slide, I will also introduce you how this platform can be built and how can be installed a bit. So it can be built both in a dry dock or directly in a platform in a quay. Then the load-out operation, of course, needs some heavy lifting operations, but it's clearly manageable. Then as is constructed horizontally, of course, then also the transport to the site for the final installation is also done horizontally, which presents some advantages also. And following for the installation, in the next slide, we can also see the appending operation. That is also one of the challenge operations during doing this in the open sea. We can, of course, we use water ballasting and a dynamic control, because this process has to be very smooth, and it's in fact there is a huge amount of tones moving, and this has to be carefully done, but in a smooth way with a dynamic control. And finally, for the installation of the turbine, we are working with a craneless technology. To summarize the concept, and before going ahead with more details of the model that you can find in Zenodo, let me summarize some of the particular advantages or properties of the Winkery concept. First, that this is a monolithic without any joint, and this is interesting in any case because it produces more durable constructions and platforms. The draft, of course, in a spar buoy is large, so normally we estimate that the minimum draft we can work with is around 80 meters, and the maximum draft that we thought that it will be reasonable from the economical point of view is around 160 meters. That is for example, for the 15 megawatt wind turbine. This can be a limit. The operational depths, of course, are consistently with the previous draft, go from 100 meters to 1,000 meters, despite, of course, the mooring system will be significantly expensive. And what is very important is that the design is adaptive, and as you will see, we can also produce a design for a 50 megabytes wind turbine. At the end, the advantage of the using a structure which is more durable and with concrete is that we can assure, for example, a lifespan larger than 50 years. And this is also very important because it reduces everything. And also the use of concrete with larger structures also produces a reduction of the capex. And then if you have a more durable one with no maintenance almost in the platform itself, this reduces also the OPEX. And at the end, all this produces a significant reduction of the LCOE. Now, my colleague, Yusuf Mahfoud, will present the details for the Gran Canaria prototype.
We can't hear you, Yusuf. I think you need to unmute yourself.
Sorry. Thanks, Clement. In the next few slides, actually, we will go through the Winkery design for the Gran Canaria site, which has a depth of 200 meters. And the draft of the Winkery spar buoy in this site will be 155 meters with a tower height, with a hub height of 135 meters. As you can see in the figure, the tower base diameter is 13.2 meters and the tower top is 6.5 meters. And for the buoy structure, it's made out of mainly 3 parts. At the top, 10 meters of a transition piece, which is a conical shape, and then we have a cylinder to give the buoyancy forces to carry the RNA assembly, the rotor nacelle assembly, and the tower. And at the bottom, we have a semi-sphere shape to decrease the pressure at the bottom of the spar floater. In the next slide, we can see the composition of the fast model. So we use the 15 megawatt IEA wind RNA without any changes. So we use the blades and the rotor and nacelle assembly, all of it, the blades, the nacelle, and the generator. And we couple it with the Winkery floater, which includes the tower, as Clement mentioned. And we have a mooring system, which is a catenary symmetric delta-shaped mooring line system to provide stiffness in the yaw direction as well as the sway and surge directions. And for the controller, we tune the Rosco controller, which is the NRR reference open source controller, and we tuned it for floating wind turbine to prevent the presence of any negative damping in the pitch direction. In the next slide, we see some natural frequencies result from a free decay test done for the OpenFast model. And we can see on the left image the surge decay, and on the right side the pitch decay, with the frequencies in hertz and second in the table below for surge, heave, pitch, and yaw. We can see for the platform, the surge decay is around 82 seconds. The surge natural frequency is around 82 seconds, and the period is around 82 seconds, and the heave period is around 33 seconds, while the pitch is around 40 seconds, and the slowest period is our yaw, which is 11 seconds. And in the next slides, we have the links for the models in Zenodo, as well as the report with the detailed descriptions for both models, ActiveFloat and Winkery, and you will receive those links in an email shortly after the presentation, and feel free if you have any kind of questions about the models to contact us. Thanks a lot.
Great. Thank you to both. That was very clear. We're now going to shift gears to focus on mooring solutions for floating offshore wind turbines and what we've been doing in the Corewind project to optimize these systems. So Valentin Aramounet from Innosea will tell us all about that. Valentin, the floor is yours.
Hello, everyone. So I will be talking about the optimization methodologies and the optimized mooring system that we did for the Corewind project. So just before jumping to the details of the different moorings, let's present a bit the design optimization methodology that we developed within the first year of Corewind project. So basically, as we were talking before about a fast model, so we get the fast model from the work package 1 and we plug it to an Arkaflex model. In our fast model, we keep the tower and the RNA that is plugged to the Arkaflex model, in which we will have the modelization of the floater and the mooring system. So we have the what I call the base model, and we will optimize the mooring system using this base model. So to do this, we plugged our fast Arkaflex model to the iSight optimization software using a Python interface. And this iSight model will iterate on the mooring design parameter, such as the anchor position, the line lengths, the line size. And if we want to use different type of lines, it will iterate on their size and their lengths on each different parts. And also, it can also iterate on clump weight and buoyancy modules if we want to integrate this. So we run one DLC, and the iSight will iterate until it reach the most optimized mooring system in terms of cost. Also, we want to respect some design criteria such as the excursion and the angle of the platform and the acceleration of the RNA. So if we jump to the next slide, we can see the case studies that we used for this analysis. So for the mooring optimization, we are focusing on DLC 6.1 and 6.2. And those optimized mooring systems are then checked for a larger batch of DLC in ULS, FLS, and ALS in other tasks. And we are also checking start of life and end of life configuration. So just so you know a bit the different configuration of the different sites. We are studying 3 sites, such as west of Barra, Gran Canaria, and Morro Bay. You can see that the environmental conditions are quite different. The depth is evolving from 100 meters to almost 900 meters, so it will affect a lot the mooring design. And you can see also that the wind speed and wave and current amplitudes are also varying quite a lot. And keep in mind that for west of Barra, you can see that the HS is really large compared to the other one, and also the wind speed is also quite high. And you will see the impact that it has on the mooring design. So jumping to the next slide, we are presenting the results for the 3 sites and for the active float floater, which is not the floater you've seen in the slides before, but which is the other floater, which is a semi-submersible floater. So for the Gran Canaria, the environmental conditions are the most, I would say, the easiest one. So we managed to find a quite simple mooring system, which is a catenary mooring system with 3 lines, which are composed of 800-meter chains. You can see that the upwind chain is a bit bigger than the downwind chains because the environmental conditions are coming from this side, and we want to optimize the mooring system, so we don't need to make it fully symmetrical. And looking at this system, we can see that we managed to reduce the price of approximately 60% compared to the initial mooring system. On the next slide, we are presenting the result for west of Barra. So as I said before, this site is a lot more complicated. So the mooring system is a lot more complicated. And what you can see that this mooring system is also a catenary mooring system composed of 12 lines. You have 6 catenary lines of upwind and 3 lines on each side downwinds. And the lines are composed of nylon, chain, and clamp weights. So the nylon is here to offer the possibility to add some elasticity in the actual stiffness of the line to dump a bit the peak loads. And then we are using some chain and clamp weight to have to create some weight in the mooring system to create what we call the mooring restoring force. So what you can see is that the lines are really long. We have more than 1 kilometer of line length, and our estimated cost is really high also, which is almost 15,000 kilo euros for this mooring system. And we have no comparison with the initial one because the initial mooring system wasn't working. On the next slide, we are presenting the mooring system for the Morro Bay site, which is a site, a deep water site. So it's a semi-taut mooring system with polyester line, which offer the possibility to have a really high stiffness, actual stiffness, and on top 50 meter of chain, and on bottom between 140 to 130 meters of chain. This mooring system was also optimized, and we can see that we managed to reduce the price of 55% compared to the initial mooring system. On the next slide, we are summarizing the comparison between the price of the mooring system. So as I was saying, in Gran Canaria, we started with a price between 2,000 and 3,000 kilo euros, depending on the chain grade. And we managed to optimize the mooring system to reduce the cost down to 900 kilo euros. For west of Barra, we don't have any comparison because the initial mooring system was not fulfilling the design criteria. And for Morro Bay, the last mooring system, we reduced the price from 1,400 down to 600 kilo euros. So this was the mooring system that we optimized for the first year, which are quite basic mooring system. And now we are starting some new tasks to look at some more complex and optimized mooring system. And to do so, if we go to the next slide, you can see that we are investigating some peak load reduction system. So on the right side, you can see that there are several systems that are currently under study. So you have the TFI mooring system, you have the IMS mooring system, and the C-Flex mooring system. So there are all three of those systems are actually providing a nonlinear stiffness, which are allowing us to dump the peak load for the most complicated environmental conditions. And their effect is also having is interesting for fatigue load reduction, because as you dump all the peak load, you will use the fatigue on the mooring system. So for example, if you look at the curve that we see below, you can see that for this example, with a wire rope, we have the tension depending on the specific height of the waves, and using those systems, we can manage to reduce quite drastically the peak loads. So it's quite promising, and we hope we'll manage to reduce the price of the mooring system using those different peak load reduction system. And also we have another parallel task, which is the shared anchors and mooring lines that we are going to start. And the goal is also to share the anchor and mooring lines at the farm level to manage to reduce also the global price of the mooring system at farm level. So thank you for listening, and I give the microphone back to Sabina.
Thank you for that, Valentin. So moving now on to operation and maintenance, we have Marie-Antoinette Schwarzkopf from Ramboll, who will tell us about opportunities in maintenance strategies for commercial scale floating wind. Marie-Antoinette.
Thank you, Sabina, and hi to everyone. I've brought you a small quote. So a physician for emergency medicine from North Carolina, Yancey Bain, once said, my experience with seasickness is that at first you are afraid you will die, and then after a few hours you are afraid you will not. So just now imagine that you have a maintenance crew falling seasick during a maintenance campaign. So this is known from boat transfer, but now the time that technicians spend in a moving environment will increase as the wind turbines are now moving too. So going to the next slide, I shortly want to introduce you to the concept of workability. When motion sickness occurs, it impairs the performance of the technicians. It might delay maintenance campaigns and therefore will also have a financial impact. This is caused then by longer downtimes or rescheduled inspections, for example. And Ramboll developed a methodology for the assessment of motion sickness on floating wind turbines in the Life 50+ project. And we are now developing it further in this project, applying it to the Winkery and active float concepts. Together with our partners, we will then evaluate the sea states in which the maintenance personnel will be negatively affected by the motions. So yeah, we can see from this example that floating wind turbines pose a new challenge and new challenges, and in general also new risks to the O&M phase that need to be approached. And yeah, so we contacted several external stakeholders, which we interviewed across the industry. And yeah, our aim was to identify the O&M requirements for a commercial scale wind farm from their point of view. You will find all the results from these interviews and from our researches in the published report on the Corewind website. The link will be communicated, I think, in the thank you email from this webinar. So on the next slide, you can see the focus areas that we discussed with our interview partners and that we focused on in our deliverable. So yeah, the first one, workability, I just talked about, but there's of course also the topic of accessibility. Yeah, to the floating wind turbine, which involves, of course, the challenge of the relative motions between the swimming substructure and the floating vessel. And this topic of relative motions also, of course, affects the topic of large component exchange, where different solutions are also here available, and I will introduce them shortly afterwards. Then we discussed the new challenges for mooring lines and power cables that might occur during the O&M phase. And last but not least, we touched the topic of subsea inspections. And here we found that new developments go rather towards resident, remotely operating vehicles with subsea charging stations, which do not require a deployment vessel anymore and are therefore less limited by weather windows. So in general, the trend of offshore maintenance goes towards a risk-based maintenance strategy, and the extrapolation of those findings of a representative wind turbine to an entire wind turbine cluster. And in this presentation, I will concentrate on the topics of the accessibility, the large component exchange, and the mooring lines. And all other findings can, of course, be read in the report. So on the next slide, I would like to highlight some of the findings on the accessibility challenges that will need to be addressed for floating wind. So one very interesting thing was that for sites in the Atlantic Ocean, swell waves are prevailing and much longer than they are in the North Sea. So this challenges now the significant wave height limits of the access systems, which are defined with an HS limit and which are also defined according to the experiences in the North Sea. So this makes the topic of maintenance-friendly design more important. And here we have one thing from the oil and gas industry. You can see it on the picture on the right side. It's a V-shaped landing zone. It acts like a funnel, and it helps the operator of the gangway to land the gangway more precisely in this funnel. So this is much easier when there's more relative motion involved. And these funnels, they are difficult to retrofit, so they should already be pre-installed as part of a maintenance-friendly floater design. Okay, moving on to the next slide. Regarding the topic of large component exchange, here we face the challenge that in general floating wind farms are installed on sites with, of course, large water depth, and here it's not possible anymore to use jack-up vessels. So we need to find new strategies for the large component exchanges. And the first one is the tow-in solution, which mainly depends on the distance to the harbor, and of course also on the harbor capacities. It also depends on how easy it is to deconnect and reconnect the mooring lines and the cables of the substructure, and of course also on the substructure type, how easy it is to tow it back. Then the second solution is to use a floating crane vessel. We call this floating to floating operation. Here the relative motions of course play a major role, and there is the solution that has been developed is a two-lift operation. That means that the relative motions are reduced by performing the lift of the wind turbine or of the component on the same reference level as the crane, and then in a later lift do a bigger lift back to the wind turbine. So this is a nice solution, which reduces the relative motion significantly. And the last solution is a self-hoisting or climbing crane. This is something that comes from the onshore industry and is currently being developed also for offshore wind. This is quite interesting because here a crane is hosted to the top of the turbine where it is installed, and then lifts the component which needs to be exchanged to the top of the turbine. And while being on the nacelle, it is on the same reference level, of course, as the turbine itself. And with that solution, we have avoided the relative motions here. So moving on to the next slide, and here picking out the topic of the mooring lines. I want to share some experiences from oil and gas. So these experiences showed that the damages occur mostly through external threats, like fishing nets, boats, seabed contact of the mooring line, or a collision, for example, of a remotely operating vehicle with the mooring line. So damages from external threats are, of course, more difficult to extrapolate to a wind turbine cluster, as it can be done for fatigue damages, for example. This is they are hard to see in advance when they will happen. So it's this extrapolation here is, of course, not so easy to do. And further, there's a second challenge. So when we have a tow-in situation, we will need to kind of park the mooring lines on the site and do this wet storage, it is called, of the mooring line on the site. So here there is, of course, the risk that the mooring line will get into more contact with the seabed, and that this will cause abrasion on the mooring line if it is the case that we have a fiber rope. Oh, these are not my slides anymore. It's the case that we have a fiber rope, and of course this is not something that's wanted. So here, of course, I want to highlight that there's also the solution to use a hybrid rope, which is a combination of a steel and a fiber rope, and they are more robust. Then moving forward to the last slide, I want to give a short outlook on our simulations that we are now performing in the current task 4.2 in Corewind. So here we use all the results, the findings from our research that I just presented to you, and we collect all these requirements and recommendations, and we now want to assess them closer in a simulation environment. So first we study the access situation of a crew transfer vessel using boat transfer and compare it to the access with a motion compensated gangway. Then we study the relative motions for a large component exchange using both a semi-submersible and monohull floating vessel. We perform these simulations in an Orcaflex environment, and you see some pictures of the simulations on the slide. Also, the towing of both floater types has been simulated in order to deduce the sea states in which the tow-in operation is feasible. All these results then feed into a cost and strategy simulation model, which is called Shoreline. This is a commercial web-based tool to simulate the O&M phase of a wind farm, and it allows to optimize the allocated resources, the wind farm availability, and the operational costs. at the end of the project, we want to identify the key levers for increased availability and revenue. So this was it from my side. I hope I could give you a short impression on new requirements in the O&M phase for floating wind. And I give the word back to Sabina. Thank you.
Thank you very much, Marie-Antoinette. That was very clear. So now moving on to Jose Ignacio Rafa from IREC. So I gather you'll be telling us a little bit about the FOAP, which is an intuitive application which we've developed in the Corewind project and to be used during early project planning of floating offshore wind farms. So tell us more, Jose.
Hello, thank you, Sabina. Well, so let's begin with the first thing, and that's answering what's FOAP. So in short, FOAP is a desktop application to assess floating offshore wind farms from two perspectives, environmental and economic. It allows the calculation of the annual energy production based on the wind farm configuration and the wind climate as the delivered energy to the onshore electrical grid. Also, an analysis of the life cycle costs can be done using this tool, understood as all the expenses incurred in the wind farm from its development until its commissioning. Based on these calculations, the application determines the levelized cost of energy, which is a common metric to compare different technologies. And last but not least, it's also useful to perform the life cycle assessment of the wind farms, which is the environmental evaluation of the technology that considers the materials used, the transportation processes, and the end of life of the farm, among others. The LCA is also a reference to a functional unit to allow its comparison to other technologies, which is in this case the electrical energy delivered. But before continuing, in the next slide, we'll step back for a moment and see why FOAP has been developed. Well, offshore floating wind farms introduce new technologies such as dynamic cables and floating substructures. Moreover, new strategies must be defined for the design, installation, and O&M, among others, as exposed by the previous presenters. Additionally, overall costs must be reduced before we see a massive deployment of the technology. So if we consider these aspects, we see that it is a complex technology and that it has many disciplines involved and lots of challenges. On the other hand, existing applications have a lack of technical detail, are not focused on floating wind, and only pay attention to the financial details, defining a gap that can be understood as an opportunity. This led to FOAP, a tool developed by IREC during the Life 50+ project, European project, in order to assess the wind farm concepts defined in such project. And eventually, it evolved to FOAP, with the purpose of performing the analysis for any wind farm, including many new features and improvements. In the next slide, we can see the concept of FOAP. It can be divided in three parts: the library, the projects, and the results. The main advantage of having a separate library is that it includes all generic data that may be used in any project, avoiding repeated definitions and allowing centralized edition of information. Such data includes the different sites where the farms may be located and the auxiliary means required during its life cycle. It's not that turbines, moorings, and substations orders are included under components. Project data is divided between the arrangement, which corresponds to the farming characteristics, and the life cycle, including the details of the wind farm from its conception until its end of life. And finally, FOAP uses this data to calculate the LCOE and LCA with also intermediate but relevant results such as the LCC, AP, and LCIA. In the next slide, we will focus on these results. The annual energy production is calculated only using the arrangement information, including the intermediate results. The subsystem's efficiencies are provided with additional details for the wakes, and the capacity factor is also calculated. Regarding the life cycle costs, a detailed analysis is performed to assess the different phases of the project. The levelized cost of energy summarizes the wind farm performance and is also calculated the effect that each phase has on it. And finally, the life cycle assessment provides the impact on 7 different categories. And this module is not yet finished, but we will consider that when we finish it. We will consider the effect of the materials used for the different components, as well as their origin, the impact of the fuel consumed by the auxiliary means, and also the effect of the end-of-life management with multiple options to be selected by the user. So in the next slide, we can see the highlights of the application. Starting with the features, we can say that it is a tool that has been built from scratch and specifically for the floating wind industry. So in this sense, is more accurate and has only the points that are relevant for the floating wind industry. It includes all the intermediate calculations, so it's not necessary to import anything from other programs, but it's a possibility. And for that purpose, some templates from Microsoft Excel can be imported. The data is stored in an SQLite database, allowing also for future development of additional tools that connect to that database and access the information which is there. Regarding the advantages, we can say that it is a user-friendly application, and that the level of detail that the user inputs is reflected on the level of detail of the outputs. So in this regard, if the user wants a high level of detail, can achieve it, and the opposite is also possible with the same tool. Also, we can say that we have multiple substations allowed in this application, such as offshore floating converter substations or transformer substations or reactive compensation substations. And that, for example, it's the first tool that combines economic and environmental analysis specifically for the floating wind. In the applications, we can find the early project management, project development, the technology assessment, environmental impacts evaluation, and performance analysis of floating offshore wind farms. In the next slide, we have 4 screenshots that are extracted from the application. In the top left, for example, there's a screenshot of the layout definition. This can be introduced manually by the user in the application, but also it can be imported using a Microsoft Excel template. On the top right, we see the graph of the electrical connection. As the user defines all the connections, the program incorporates a system to verify that the final electrical system is correct. And multiple connections are allowed, and multiple nodes, including possibilities to, for example, subsea connection hubs and other features that maybe nowadays are not usual, but maybe in the coming years will be used for sure. In the bottom left, for example, we can see the summary of the test data, but the summary of a project in which the user can see all the selected anchor system, the mooring system, the turbines, the sum of lengths of the cables, and so on. And finally, in the bottom right, we can see an example of one of the output screens, in this case of the annual energy production, in which it can be seen the ideal energy production and all the losses that are caused by the electrical conductors or wakes or substations, And finally, the electrical energy delivered to the onshore grid. We can also see the annual energy production and other results. For example, in the middle, you can see a chart or a table with the efficiency of the wakes depending on the wind speed and the wind direction. And in the next slide, we can see the next steps that we expect in the development of this application, such as the first one, which is already ongoing, that is the registration of the application. Then also the LCA module, as I said, is still under development, but we are finishing it and will be ready soon. Once we have done this, probably next month, we'll start the testing of the full application. And once that's done, the first use of this application will be the Corewind project to compare the initial reference scenarios defined and the final concepts and output by the different partners. So this way we can check and calculate the difference of the LCOE, for example, between the initial designs and final designs at the end of the project. And finally, the commercial deployment is expected to be by the end of this year. Okay, so that's everything from my side. And thank you for your attention.
Thank you very much for that, Jose. It sounds like a very useful tool. And finally, as mentioned at the beginning of the webinar, we have with us today a special guest, Pablo Necochea from Vestas. So Vestas is not part of the Corewind consortium, but we were very keen in getting the point of view of a wind turbine manufacturer on the usefulness of innovations like the ones in the Corewind project. So Pablo, the floor is yours.
Thank you very much, Sabina. Let's start with the next slide. So first off, a bit of a corporate intro here. Vestas addresses the full value chain from design and manufacture through to the installation and service of the wind turbines. And as of February 1st, this is both onshore and offshore, as Vestas recently acquired MHI's shares of the MHI Vestas joint venture, which increases our focus on the offshore market. But we continue with our innovation journey. We will continue to do more floating offshore wind projects, and we have launched the V236 15 megawatt. Vestas has embraced floating offshore wind since its early days, and we have gained significant experience in this path towards commercial scale floating projects. But to continue down this path, the collaborative approach is critical because floating requires significant interaction between all parties. So strong partnerships are coming to be key. Let's go to the next slide. Our experience began back in 2011 with the WindFloat 1, where a second-hand V80 Vestas turbine was put on a principal power floating foundation. I think it might have been the prototype, and it was run for all of 5 years, so from 2011 to 2016. In that time, it produced 17 gigawatt hours, and it survived a storm with 17-meter waves and kept producing even under 12-meter waves. So WindFloat 1 proved to be very valuable for us because we were able to demonstrate various things. On the one end, we demonstrated that our modeling approach was right. So we demonstrated that the dynamics of the system and the verification of the model responses were correct. And it allowed us to check that the wave and wind induced loading that we had seen originally was actually as modeled. Finally, we participated in the decommissioning of the unit, and that allowed us to evaluate the condition of a turbine after 5 years of operation on a floating foundation. Cool thing about that is that upon realizing that no significant degradation was suffered by the turbine, it gave us the confidence to go for bigger, better, and braver projects. Let's go to the next slide. So we're currently working on more demo projects with different site conditions and a larger variety of floating foundations. We've been quite busy in Portugal and Scotland in the past year and a half with the Windfloat Atlantic and the Kincardine projects. And our first projects in France with a preferred supplier status are the Grand Belle-Île project, the EFGL project, and EolMed. And all of those will benefit from V164 turbines, this time on different floating foundation types. So we're looking at a couple of more demonstration options, but I think it's fair to say that we need to find a balance between this high demand for further demonstration projects and engaging into commercial scale applications. So, demonstration projects have proven to be very resource intensive, and we need to select those going forward that will add the most to both the company and the industry. But the time has come to step up into commercial scale projects. Because it's the only way that will really demonstrate the competitiveness of floating offshore wind. Can you go to the next? So how do we go about designing? It's one of the differences with fixed bottom offshore is exactly this integrated design process, because it is considerably longer, it has more iterations, and there is a substantial amount of cross-functional collaboration between the developer, the floater designer, and the turbine OEM. We generally begin the projects with a high-level evaluation of whether the floating foundation concept designed for those site conditions will present a risk to the turbine or not, in its interaction with the floater, of course. Then we will build an integrated turbine floater model into our in-house software called Vestas Turbine Simulator. And then we run a model verification test cases. This process is iterated until the integrated model is then verified, and we can begin the coupled load simulation. We do this using metadata. We use the floating foundation and the turbine failure modes, along with some wind data and a modified turbine controller. It's quite similar to what Corewind has proposed. The design loop will go through a few iterations and until the design has been optimized. That means that the loads are acceptable, the floater is not excessively sized, and the energy loss is at a minimum. So given this long and resource-intensive design process, it's very important for developers and floater designers to engage with OEMs at a very early stage of the project, as early as possible. Because there's just so much optimization to be done that you really need to take the time to look at it. Let's go into the next one and wrap up. So yes, floating is coming, and it will step up to the challenges ahead on this path to a competitive LCOE, and it will become an important and complementary part of the energy matrix. So demonstrators have helped to mature the technology. They have showcased floating's potential to lenders, to insurance companies, and to developers. But as an industry, we will not secure that promised outlook of a low LCOE, this low LCOE that we're discussing in the Corewind project, if we continue to entertain this pangent diversity of floater types. We need to get what we have. We need to take the experience that we have and deploy it at a commercial scale. If floating is to have a future, governments also need to step up. They need to provide the policy that Lisette mentioned. They need to provide leases and some form of subsidy to give momentum to that cost out curve so that we can achieve the cost out level at which we will be competitive, not with fixed bottom offshore, but with onshore grids. So floating also needs credibility. And I think that's one of the things that the Corewind project really, really supports us on, because they, as an industry, we're committing to a cost out. And there's plenty of ideas out there, and there's plenty of innovations coming out. And each one of those is a building block on this path to a competitive LCOE, or to reaching the onshore grid. For example, we're already seeing serialized and industrialized manufacturing processes for putting together the floaters. So each one of those different elements throughout the supply chain needs to be put together in one bird's eye view system, and that's where Corewind comes in, because Corewind provides the means to model, quantify, and demonstrate that these building blocks that are out there have an impact on the overall LCOE of floating offshore wind. And they address all the innovations from across the supply chain, and it allows the industry to then quantify the collective impact of cost outs and its overall impact on the LCOE. So, yeah, I think I'm out of time, but I thank you very much for the opportunity today to present our view.
Thank you very much. Thank you very much, Pablo. And good to hear your perspective on what is needed to release the full potential of floating, and also that what we're doing in the Corewind project is somehow useful to that. So indeed, we can now go on to the questions. We actually have quite a few. Starting with a question for Lisette. Lisette, we have a question for you on, can you elaborate on how the pipeline of floating projects will deliver the projected cost reduction, which we're always speaking about?
Thank you very much for the question. And yes, of course, I was mentioning the pipeline is worth at least 7 gigawatts. This is because we consider, first of all, well, to connect it also with the cost projection reduction, the first pre-commercial projects or demonstrators of arrays were at a cost of slightly over 200 euro per megawatt hour, okay? This is of course higher than bottom fix, and we know that at the moment because floating is developing now. However, if we take a look now at France, France has one of the most ambitious plans to deliver floating wind farms. And actually this year is the first commercial auction for 250 megawatts at a cost of 120 euro per megawatt hour. And we estimate that this site that will be auctioned this year, and there are 2 more coming next year, they will of course be installed in around, I would say, 6 to 7 years from the moment they are auctioned. So that is already connecting the dots. And now there is also, I was mentioning the UK, and Norway will also play a role, because Norway is opening 2 areas, and both of them have actually sites suitable for floating. So one of it, that is 1.5 gigawatts, will be fully dedicated to floating wind. And then in terms of the UK, we see that from the current target of 40 gigawatts of offshore wind by 2030, 1 gigawatt is all floating wind. And they already changed the regulation, so they will allow that floating wind has a technology-specific pot, or a separate pot, where they're going to be competing only against other emerging technologies. So this is, of course, also helping on reducing the cost, and more or less, this is how we will deliver on the cost reduction. Thank you.
Great, thanks for that. Then I have 2 questions for Jose Luis. So the first one on tools and results availability, which you discussed, giving the overview of the Corewind project. So I think this is quite important for the audience. So all the results, the models, the tools that you mentioned, will they be available for everyone outside the Corewind project consortium? That's the first question. And then the second one on reaching technology readiness levels. So what are the expected TRL levels of the research performed, and how would it be achieved?
Okay, thank you for that question. Well, in fact, that not all the innovations or all the models or all the developments will be available. I mean, we will have some of those really public. So we are trying to maximize what can be done public, coming from data, coming from models, and coming from reports. But of course, there are some innovations that cannot be really disclosed at some point. So those ones won't. But if, as I said during the presentation, please, if you can check, I mean, from time to time, our website, you will see that we are uploading quite a lot of reports and quite a lot of models and so on, and they will be really helpful. At any case, feel free just to reach up, I mean, you, Sabina, or myself, in case there is any special interest, and we can look forward or try to see how we can manage that things. Then regarding the tier level, as I said, that project is really a research and innovation action. So our tier levels are expected to reach, let's say, tier level 5 or so. So we are reaching that levels by making some lab testing within the laboratories on IHA Cantabria. Okay, so there are where we will make some tests for the moorings, for the floaters in small scale prototypes, and also for some of the materials we are making tests in the real sea in Cantabria, also in El Bocal. Okay, so we will also want to test which is the biofueling and so on that will be happening for that materials that we are aiming to apply later on cables and moorings. Okay, so, and I think that more or less I answered the question, so thank you.
Thanks, Jose Luis. Yeah, we have a question for Clement. So the question is, what would be the main differences between the O&M for a regular 2 sections, so tower plus floater, compared to your Winkery single spar unit? Clement. We can't hear you. I think you need to unmute yourself.
Thank you. First I would like stating that any joint in a structure is a weak point. So as we can remove as much as we can any point of weakness, this is always good. Of course, this has advantages and disadvantages, because then you have to work with much more larger elements, and this is challenging also. So this is a balance. However, when you are in a very harsh environment, as we have offshore, at the end, removing any point that you have to control and inspect periodically is an advantage. In addition, the interface between 2 different materials and construction building technologies, like is the concrete one for the floater and the steel one for the tower, makes the joints quite challenging. Because, for example, in steel structures, we are used to talk about millimeters, but in a concrete structure, we talk about centimeters. This looks, apparently, is not so important or perhaps difficult, but in fact it is. Because if you have, for example, in the case of the Winkery or the floater that for Gran Canaria, for the 15 megawatt wind turbine that you have at the base of the tower around 10 meters of diameter, this is huge. 10 meters is a very long distance. Think about the length of the circumference that you have at this point. Then also from the CapEx point of view, so the investment, this is a difficulty for the construction process. However, then you have to deal with a very large element and put it in vertical position. That is also a challenge. So there is a balance between them. But at the end, as much as we can, removing any weakness point from a structure is always welcome. Thank you.
Great, thank you for that. We have a question for Valentin. So what do the presented costs include? Material, installation, logistics, installation spreads? That's the question.
Yeah, actually the cost does not take into account the installation cost, because for now it's still under investigation in the other work package. So we just have to keep in mind that for now those costs are used for comparisons between the different mooring systems that we provide. But yeah, there is no installation cost in the cost. But also what we see when we do the mooring optimization is that the more you reduce the size of the chain, the less the price will be. So basically it will also optimize the installation cost. But of course, when we'll have those cost function, we can integrate it back in our optimization software, and we can do the exercise again to check if it's giving still the same mooring system.
Okay, thanks. And then for Marie Antoinette, we also have a question for you. What main components did you consider for large component exchange, and which one have the highest failure rate?
Yeah, thanks. Thank you, Sabina, for the question. So for large component exchange, we are considering the blades. We are also considering the possibility of exchanging the entire rotor nacelle assembly. We are considering exchanging the drivetrain, for example, or so these are mainly like those bigger components, but it's of course also interesting looking at the fact that, as I said, like the larger, like the entire rotor nacelle assembly might be a solution in the future, because it's a very delicate operation when done offshore to exchange only some components. So it might be an idea to exchange the entire assembly. To the failure rates, we are currently basing our study on publicly available failure rates from literature. It is of course really hard to get failure rates because they are quite confidential, and so it's we will definitely publish the failure rates we are using in our deliverable. So at the moment, as we are just starting our simulations in Shoreline, where those failure rates will be used as input, we are currently discussing those still, and because we have a few sources available, and it's of course also difficult to find failure rates for the bigger scale, because if they are available, they are normally available for maybe 2 megawatt wind turbines, or so something that's out of the scale that we are using here for 15 megawatt. So we are still discussing those, and who's interested in those failure rates that we're using at the end, we will publish them in our deliverable, which will be online on the Corewind website in end of August. So yeah.
Great, thank you very much. And then 2 questions for José Ignacio Rafa on the FOAP. So the first one is, what advantages does the FOAP application have compared to other tools? And the second one is, so is this application expected to be available online, or what plans are for the future use do you foresee? José?
Okay, well, regarding the first question, if we see the different applications that are available for the LCOE calculation, we see that most of them are more focused on the economic aspects rather than on the technical aspects, and that's one of the advantages of our application, because we think that that leads to higher accuracy of the energy delivered to the grid. Because, for example, we integrate the wake calculations in the tool, We don't estimate the electric grid losses. We calculate them using power flows and other reasons. And that's one thing. Additionally, for example, this application is only for floating wind, and other applications are for a broader number of technologies, and this one is specific, so we understand that that's also good. And finally, of course, we are coupling the LCA with the LCOE in the same application, and LCA tools are typically generic and calculate the environmental impacts, but we don't know any application that performs the LCA specifically for the floating wind. And regarding the second question, the plans now, of course, they may change in the future, but now the idea is to finish the tool. By the end of the year, we could have the tool fully working and we could start the commercialization. The idea we have now is having two versions, maybe one demo version that would be for free for anyone, and then the complete version with all the features, but that would be should be purchased.
Great. Thanks a lot, Jose. And then I have two final questions for Pablo. The first one being, how can wind turbines contribute to reduction of the LCOE? Is bigger really best on floating? And then the second one, so from the OEM's point of view, which floaters will drive the commercialization of floating offshore wind? Pablo?
Okay, the first question with regards to whether larger rotors are best for floating, it depends a lot on what floating foundation type you're going with. Some floaters scale very well with larger rotors. Others just add steel mass to the original design to a point where it's just not commercially competitive. But generally speaking, the semi-submersible scale very well with the larger rotor. So we do expect to see an improvement of the LCOE curve when it comes to using next generation turbines. And the other question had to do with?
So which floaters will drive the commercialization of floating offshore wind from your perspective?
I think we need to take advantage of this momentum that we've built right now. Most of the floaters that we see today are not really designed for mass manufacturing, but the next generation are. So we need to take advantage of what we have proven today and what has been demonstrated today to fill that path to the end of towards the end of the decade, so that by the time we're installing those very large commercial scale projects in 27 onwards, we can use the next generation of floaters and deploy them at a rate of manufacturing that satisfies the need for size. One more point that I didn't mention on the larger turbines is that another constraint that needs to be taken into account considerably is the port infrastructure available in these markets, because floating is being deployed or is being planned to be deployed in markets that may not be suitable for offshore wind in terms of their port infrastructure. And it's important to consider what those limitations are before committing to a very heavy and large turbine that perhaps will not be able to be installed at that port.
Great, thank you very much. Just on time, actually, we have 1 minute left. So just wanted to thank you all for joining us today, to you speakers, but also to our participants and for your questions. So I do hope our conversations today have been valuable and useful to you. So do follow us on Twitter and LinkedIn for updates on the project. As we can see, maybe if you can put up the last slide. And obviously also you can find other information, as we already mentioned, on our Corewind website, corewind.eu. And you will also be able to access the recording of the webinar on the website. So thank you very much, and have a nice afternoon, everyone.
Thank you.
Bye.
Thank you.